Okay, we're back to solve the next problem. Um, the problem that is given to us now is question number 4. 120 slash 480 volt 10 kVA two winding transformer is to be used as an auto transformer to supply 480. So this is the two winding one. Let me just put it here. And then it's going to be used to supply 480, right? So this is the secondary side, and this is also my output, which is 480 volts. That's the output, and this is 120 volts. And now I'm going to connect a series uh, wire. Now this is from a 600 volt. So I hope you know why it is from a 600 volt. So the combination of the voltages on the primary side and the secondary side is 600 volts. So this is going to be my uh, my voltage on the primary side of the auto transformer. So let me just draw it. So this is something that looks like this. Uh, Now the output, which has a voltage VC, is 480. And here I'm going to have 600 volts, and this one will be 120 volts. Okay, this current is what we call I high, this current is what we call I low, and because this is a step down uh, auto transformer, the current IC will be going up because we expect I low to be the sum of I high and IC, because in a step down transformer we expect the voltage to be lower, and that's the case here. So you can see that 480 is lower than 600, but it is actually the opposite when it comes to the current. So we expect to have a higher, so we expect I low to be higher than I high, and this is the relationship. Okay, now when it is tested as a two winding transformer at rated load, so let me just explain rated load. Rated load means 100% of the load, right? So if they say 50% of the load, uh, it means that your your power, which in this case is 10 kVA, will only be half. It will only be 5 kVA. So when they say at rated load, right? At rated load, so it only means that the value of that load is actually 1 or 100%. Unity power factor, okay? And this two winding is operating at unity power factor. So remember, power factor is what we call cos phi, which is the angle between the applied voltage and the applied current. So that's cos phi. So it's unity power factor. Unity power factor means 1. So that means that the angle here, I mean, even though it's not part of the problem, I'm just showing you that if you do the cos inverse of 1, you get 0. Yeah? So when we say that we have unity power factor, it simply means that the voltage and the current, if you're dealing with the phasor diagram, the voltage and the current are in phase. They are both at 0. Okay. Now its efficiency is 0.979, and this is per unit, right? So that's the efficiency, which is this is about 97.9% in percentage. In per unit, it is 0.979. Now we need to understand what efficiency of a two-winding transformer is equal to. So the efficiency of a two-winding transformer is nothing but, so we use this symbol here, it is like this for efficiency, is the power output over the power input. So this is the efficiency of a transformer. So if the transformer is a two-winding transformer, then we say that the power output is equal to the power input. So we are not given any information about the power input, but we know from our knowledge of physics that if you want to know the input power, you just need to know the output power and you add the losses, right? So input power is nothing but the power output plus the power losses. So this is now the formula that we'll be using. So efficiency will be given as power output divided by power output plus power losses. So how do we get the power losses? Well, efficiency is given to us. So if we know the value of efficiency and we know the power output is given because, of course, the rated power and the power factor will give us the power output. So power output can be written as S output times the power factor. So in this case, we are saying this is 10 kVA times 1, which is simply 10 kilowatts. So this will be the power output. Okay, now let's focus on the problem itself. So the first one, they want us to determine the kVA rating as an autotransformer. So we know the formula. This is the picture. So the kVA rating of the autotransformer, which we call SIO, is equal to SW, and this is NSE plus NC divided by NSE. And remember, the number of turns and the voltage ratio are equal. So then I can call this VSE plus VC divided by VSE, and SW is given to me as 10, and then VSE plus VC, so this is VC, this is VSE, so it's 120 plus 480, that's 600, and then VSE is 120. So if I use my calculator here, this is nothing but 10 times 600 divided by 120, and I'm getting 50. So I'm getting 50 kVA. So this is the power rating as an autotransformer. So if we have an autotransformer with these connections, we expect the power rating to be 50 kVA. So now that we know the power rating of the autotransformer, let us now solve this question here. Determine the percentage power efficiency of the transformer of Q4 when operating as an autotransformer. So the first thing we have to do is we have to find the power losses of this transformer when it is still a two-winding transformer, because the power losses is nothing but the copper losses. So when you connect a two-winding transformer as an autotransformer, the copper loss is still the same. So all we have to do is find the copper losses here and then use a new efficiency formula and find the efficiency as an autotransformer. So let's do that. Okay, if I have this formula, and let me call it the efficiency. Let me call it the efficiency as a two winding. So NTW. So the efficiency is a two winding, which is the power output divided by the power output plus the power losses. And this efficiency was given to us as 0.979. So all I have to do now is make P losses the subject of the formula. So this implies that P output, and then if I do my cross multiplication, I have P output plus power losses. Yeah? Cross multiplication. Now I need this as the subject of the formula. So if you're very good in mathematics, you multiply out and then you combine like terms and then you get that P losses is equal to, so you multiply out P output, and then you are going to have something like this. P output 1 minus the efficiency as a two winding divided by the efficiency as a two winding. So now let me simply plug in the values here. So I have the power output as a two winding, which was given here as what? 10 kVA times the power factor, which is unity. So it's 10 times 1. So that's the power output, or 10 times cos of 0, which is 1. So power output is S output times the power factor times 1 minus the efficiency as a two winding divided by the efficiency as a two winding, which will give me 10 times 1, right? So it's 10 times 1, unity power factor, 1 minus 0.979 divided by 0.979. And this will give me the power losses or the copper losses. So let me just take my calculator quickly. So that is 10 times 1 minus 0.979 divided by 0.979, and I'm getting 0.215 kilowatts. So I'm getting 0.215 kilowatts, because remember the power here, I'm saying 10, but it's actually 10 kilowatts, or 10 times 1 kilowatts. So in kilowatts, my power loss is 0.215. Now that I have my power loss, I can now come up with a formula to find the new efficiency. So the formula to get the new efficiency, or the efficiency as an autotransformer, which is the efficiency as IO, is the same. It's power output divided by power output plus power losses. So the power output of an autotransformer is no longer 10, is now 50, because when we have done the calculation, it is now 50. And then if you look at the problem here, they say when it is operating as an autotransformer at full load with 0.85 power factor lagging. So now the power factor is no longer 1, the power factor is now 0.85. So let's find what the efficiency of this will be. So the power, which is 50 kVA, times the power factor, which is 0.85, divided by 50 times 0.85 plus, maybe the question is, why am I multiplying by 0.85? Remember, this 50 is S. So now I have like S output multiplied by the power factor, and this is what gives me a quantity in watts, because watts is actually the real component of your apparent power. So that's why I have to say 50 times the power factor plus the losses. So the losses are still the same. So it is the same transformer, only that it is now connected as an auto transformer. So the power losses is still the same, and the value is 0.215. So now let me take my calculator and do this, right? And find this efficiency. So it's 50. It's 50 times 0.85 divided by 50 times 0.85 plus the losses, which is 0.215. When I do this mathematics, I'm getting 0.994, 0.994, 9949, 9949, something like that. And in percentage, this is about 99.49% or 99.5%. And if you look at the problem that I've given to you, that's exactly the answer they got here. So it's 99.5. That is the efficiency of this auto transformer. Okay. Now question number 6. Let me see if I can do it right now or whether I should post for the next one.